Laser powder bed fusion utilizes a laser to melt a pattern in a thin layer of powder. The process is shown in the schematic on the lower left. The build platen is lowered and powder is fed from a powder trough and doctored into a thin layer on the build platen. The thickness of this layer is typically 30 to 100 microns depending on the surface resolution needed and the build speed needed. A laser beam is guided by a CNC controlled galvanometer mirror to raster across the build plane. The powder is melted raster by raster, so the entire pattern's area must be scanned. Once the layer is complete, the build platen is lowered again, powder is doctored on, and the lasing process begins again. This is repeated as many times as it takes to build the entire height of the build. On the right is a photograph of the process in action. The outside perimeter is scanned first, and then the interior is filled in. This strategy is used to establish and fix the part tolerance as the volume taken up by the melt powder shrinks during the melting. This confines the shrinkage to the Z direction, which is accommodated by the next layer of powder. If the scan was started in the center and worked outwards, then XY shrinkage would have to be accommodated as well. Here are some examples of parts that have been made by laser powder bed fusion. The materials include F75, a cobalt chrome alloy, nickel-based superalloys, stainless steels, titanium, even precious metals. In the lower left, the mesh portion on the bottom of the part is build support. It's not part of the item. We'll address this later, but the spoiler is that it has to be removed. In the upper right, the part on the top is a bracket designed for and made by traditional methods. The lower bracket is designed using topological optimization, that is, putting support and strength just where it's needed. It's efficient, but difficult to make via traditional manufacturing methods. The part in the top center has been cut in two to show its cross-section. The internal channels are very complex. The idea here is that these items would be very difficult or impossible to manufacture using traditional manufacturing methods, and this is a strong point of additive manufacturing.